Close your eyes for a moment. Listen, not with your ears, but with your imagination. Can you hear it? A low hum, growing in pitch and volume, a cosmic crescendo that ends in a final powerful chirp. This is not sound as we know it, it's the sound of spacetime itself, screaming under unimaginable stress. It is the final song of two of the universe's greatest monsters in their last deadly embrace. We are about to witness the most violent, most energetic event since the Big Bang, the merger of two supermassive black holes. It's a process that happens in deafening silence, yet its impact is the loudest thing in the cosmos. Join us as we pull back the veil on this cosmic cataclysm and journey to the heart of the storm. Before we witness the collision, we must first understand the Titans themselves. At the heart of nearly every large galaxy, including our own Milky Way, there lurks a monster, a supermassive black hole. These are not the stellar mass black holes left over from dying stars. These are behemoths, millions, or even billions of times the mass of our Sun. They are the gravitational anchors of their galaxies, the silent rulers around which everything orbits. But galaxies are not islands, they are travelers in the cosmic sea, and sometimes their paths cross. Pulled together by the relentless force of gravity, two galaxies can begin a slow, beautiful, and chaotic dance of merging that lasts for hundreds of millions of years. And as the galaxies collide and merge, so too are their central black holes set on an inevitable collision course. Our story begins not with a bang, but with a slow gravitational pull across millions of light years. Picture two majestic spiral galaxies like our own, Milky Way and Andromeda, destined to meet. Computer simulations show this as a ghostly, silent ballet. They approach, their outer arms of stars and gas beginning to feel the other's presence, stretching and distorting in a cosmic tide. As they pass through each other for the first time, they barely collide in the traditional sense. The space between stars is vast, but gravity is a powerful artist. It rips long, beautiful streamers of stars and gas from the galaxies, creating what astronomers call tidal tails. Imagine these brilliant arcs of light painting the darkness, a visual record of the immense gravitational forces at play. After this initial pass, the galaxies pull back, but they can't escape. Gravity ensures they will fall back towards each other again and again in ever-tightening loops. With each pass, their distinct spiral structures are shredded. They bleed into one another, their shapes blurring, slowly forming a single, larger and more chaotic galaxy. Imagine a time-lapse of this process, two beautiful spirals dissolving into a single, glowing orb. Deep within this newly forming galactic core, our two main characters, the supermassive black holes, are now residents of the same city of stars. But they are still far apart, separated by thousands of light years. They orbit the new center of mass, each still holding on to its own entourage of tightly bound stars, like two rival monarchs in a newly conquered kingdom. Now, a crucial question arises: how do they find each other in this vast, chaotic space? The answer is a process called dynamical friction. As the heavier black holes move through the sea of lighter stars, their gravity pulls the stars into a wake behind them. This dense trail of stars then pulls back on the black hole, slowing it down. Picture a boat moving through water, creating a wake that creates drag. This cosmic drag causes the black holes to sink, inevitably, towards the center. After millions of years of sinking, the two supermassive black holes finally find each other. They capture one another in a stable orbit, forming a binary system. The cosmic waltz has truly begun. At this stage, they might be separated by a few light years, a vast distance, but gravitationally, they are now bound together for eternity. Imagine two brilliant points of light, their accretion disks glowing fiercely, beginning a slow, patient orbit. For a long time, their dance is slow. Their primary way of getting closer is by interacting with the stars around them. As a star passes near the binary pair, it's often captured and then flung out at incredible speed, like a stone from a slingshot. This is a gravitational slingshot, and each time a star is ejected, it carries away orbital energy from the black holes, allowing them to inch closer together. The visual here is of stars being violently ejected from the galactic core. But this process has its limits as the black holes clear out all the nearby stars, their dance stalls. They are now perhaps 1 parsec, a little over 3 light-years, apart, and there are few stars left to interact with. For decades, this was a major puzzle for astrophysicists known as the final parsec problem. It was a myth of sorts, a belief that they might never get close enough to merge. But the universe has another tool at its disposal. The solution lies in the cosmic fuel that still surrounds them: gas. The newly merged galaxy is rich with clouds of interstellar gas and dust. As this material funnels towards the center, it begins to fall towards the binary black holes, forming vast, glowing structures around them known as accretion disks. Picture 2, spinning, luminous records of superheated plasma orbiting each other. This gas acts as the ultimate cosmic brake fluid. The black holes, moving at high speeds through these dense gas clouds, experience a tremendous amount of drag. This friction robs them of their orbital energy far more effectively than flinging stars ever could. We can visualize this as streams of gas flowing between the 2 black holes, creating a turbulent, glowing bridge that saps their momentum. With the help of this gas, their separation shrinks dramatically, from light years to light months, then light weeks and light days. Their orbital dance accelerates, turning from a slow waltz into a frantic spiral. The universe is now setting the stage for the main event. A visual of their orbits tightening and speeding up like water spiraling down a drain would be perfect here. It is at this point that a new force comes into play, one that will dominate the final act. As these 2 colossal masses whip around each other at incredible speeds, they begin to stir the very fabric of spacetime. They start radiating energy away, not as light but as gravitational waves. Imagine the surface of a pond, and our 2 black holes are 2 fists spinning around each other, sending out ripples in every direction. These are ripples in reality itself. What are these gravitational waves? They are a core prediction of Einstein's theory of general relativity. He imagined that space and time are woven together into a single fabric. Massive, accelerating objects don't just move through this fabric. They warp it, they bend it, and they can make it ripple. The classic illustration is a bowling ball on a rubber sheet, but now imagine 2 bowling balls spinning around each other, creating a continuous train of waves. This radiation of gravitational waves is incredibly inefficient at first, but as the black holes get closer and move faster, the energy they pour into spacetime waves grows exponentially. Soon, this becomes their primary method of losing energy, a runaway process. They are now locked in an in-spiral, a death spiral powered by their own gravitational symphony. The visual of the spacetime grid rippling more and more violently becomes key. And this symphony has a sound. If we could translate these gravitational waves into audio, we would hear a low-frequency hum. As the black holes spiral closer and faster, the frequency of the waves increases. The pitch of the sound rises. This is the famous chirp that observatories like LIGO listen for. Imagine a waveform on screen, its waves getting tighter and taller as an accompanying sound goes from a low bass hum to a high-pitched whoop. The effect on the immediate vicinity is mind-bending. The space-time around the binary is being violently stretched and squeezed with every orbit. If you were nearby, you would be elongated and then compressed, over and over. Time itself is also affected, ticking slower and then faster with the passing of each wave. We can visualize this with a grid of clocks and rulers around the black holes, all distorting in a rhythmic, violent pulse. While the gravitational show is invisible, the electromagnetic one is not. The gas in the accretion disks, caught in this gravitational blender, is compressed and heated to unimaginable temperatures, millions of degrees. It shines with ferocious intensity, often outshining all the hundreds of billions of stars in the host galaxy combined. Picture the scene. 2 dark hearts surrounded by a maelstrom of light, a blaze of glory before the end. This brilliant spectacle is believed to be the engine behind some of the most luminous objects in the universe, quasars. These are galactic cores that are so bright they can be seen from across the observable universe. It's not the black holes themselves we see, but their final, violent meal. This is not a myth, it's a leading theory explaining these cosmic beacons. We debunk the idea that black holes are only about darkness. We now enter the final minutes. The two black holes are separated by only a few hundred kilometers. They are whipping around each other at a significant fraction of the speed of light. The distortions to spacetime are no longer subtle ripples, they are tsunamis. The laws of physics are being pushed to their absolute limits in this cosmic laboratory. Here, time dilation becomes truly extreme. Near the event horizons of these black holes, time is ticking incredibly slowly compared to the outside universe. From our distant vantage point, their final orbits would seem to stretch out, getting slower and slower, a phenomenon known as gravitational redshift. A visual of two clocks, one near the black holes and one far away, showing this dramatic difference in the passage of time, would be powerful. And then it happens. The point of no return. The individual event horizons, the boundaries from which nothing, not even light, can escape, touch. They merge. In a fraction of a millisecond, the two singularities, the two separate entities, cease to exist. A new single event horizon forms around both of them. Visualize two black spheres touching and flowing into each other, forming a single, distorted, larger sphere. Misshapen and unstable, it quivers, and misshapen and unstable. It quivers and vibrates violently, like a bell that has just been struck. This phase is known to physicists as the ring down. Imagine a drop of water falling into a still pond, creating those final, oscillating ripples. The new black hole does the same, but with space-time. To achieve a stable spherical shape, the new black hole must shed all of this violent energy and instability. It does so by emitting a final, powerful, and relatively simple burst of gravitational waves. This is the ring-down signal. It is the new Titan's birth cry, a signal that tells us its final mass and spin. The visual is of a final, powerful pulse of waves radiating outward as the wobbly black hole settles into a perfect, serene sphere. A new, more massive, supermassive black hole now sits at the center of the galaxy, but if you were to measure its mass carefully, you would find something strange. Its mass is slightly less than the combined mass of the two black holes that created it. Where did the missing mass go? The discrepancy is not small, it can be the equivalent of several suns. The answer lies in Einstein's most famous equation, E equals mc squared. The missing mass wasn't lost, it was converted with perfect efficiency into pure energy. This energy was radiated away in that final colossal burst of gravitational waves. In that split second of the merger, more energy was released than by all of the stars in the observable universe combined. A silent flash, visible only to gravitational wave detectors, that momentarily outshone everything. The story isn't quite over. The merger is rarely perfectly symmetrical. If one black hole is slightly larger, or if they are spinning at different angles, the emission of gravitational waves will be stronger in one direction than another. Like a rocket engine, this creates a net thrust. This phenomenon, called a gravitational wave kick, can send the newly formed black hole flying. Imagine the new black hole being booted out of the center of its own galaxy. This leads to one of the most incredible possibilities in astrophysics, a rogue, supermassive black hole. A monster weighing billions of suns, hurtling through the desolate void between galaxies at thousands of kilometers per second. It would be an invisible wanderer, a king without a kingdom, detectable only by the wake it leaves in the sparse intergalactic medium or the stars it may have dragged along with it. Back in the host galaxy, the effects of the merger are profound. The immense energy released, both in light from the accretion disks and from the merger itself, can act like a cosmic tsunami, It can heat up and blow away the remaining gas from the galactic core. This star-forming fuel is ejected, effectively shutting down the birth of new stars in the galaxy's center for millions or even billions of years. So how do we know any of this is real? We don't see it with conventional telescopes, we listen to it. Observatories like LIGO and Virgo are not telescopes, they are gigantic L-shaped interferometers. They use lasers to measure infinitesimally small stretches and squeezes in the fabric of space as a gravitational wave passes by. A visual animation of a laser beam being distorted by a passing wave is the best way to explain this. And why does this all matter? Because each and every black hole merger we detect is a confirmation of Einstein's century-old predictions under the most extreme conditions imaginable. It's a new window onto the universe, allowing us to witness events that are otherwise invisible. It helps us understand how galaxies evolve, how the largest structures are built, and the fundamental nature of gravity, space, and time itself. So we have journeyed from a graceful dance of galaxies to a violent final collision. We have witnessed the birth of a new cosmic titan, forged in a silent scream that warped the very fabric of reality. These mergers are not just endings, they are a crucial part of the cosmic life cycle, a process of creation through destruction that builds the universe we see today. From two comes one, and in that union a story is written in the language of gravity, a story we are only just beginning to learn how to read. Thank you for taking this journey with us into the heart of the universe's most powerful events. What other cosmic mysteries would you like us to explore? Let us know in the comments below. And if you felt the gravity of this story, be sure to like and subscribe for more journeys into the deep.